So in this video, we will introduce the two probably most important cache design parameters that you have to deal with when you would like to come up with an effective cache implementation. First, we look at cache size. So if you would like to have design a cache with more capacity than what you've seen before, for example, you have more than 28 friends you would like to put in your address book, what you have to do is, make space for it somehow. And in this example, the address book example, assuming we can only have one name per page in the address book, what you will have to do is to change the index function. You need more pages in your address book. So here we use an index function with 2 letters, which means we can now fit 784 entries in our address book. It's very similar when we would like to change the size of the cache. So now let's look at this design example here, which is a 1 megabyte cache instead of the 4 kilobyte cache that we looked at before. So the first difference you can see here, well, the picture looks the same, it's just the numbers are different, is that we need 256K entries because we have 4 bytes per entry, 1 word per entry, and we wanted to fit 1 megabyte in this cache. So that takes 256K entries, which means that we need more index bits. Instead of 10 index bits in the previous example, we now need 18 index bits. Since we have more index bits, that means that we have fewer address tag bits, and we compare that with fewer bits of the address. Otherwise, the cache design looks the same. So a much larger cache, similar design. Overhead now is smaller because as we increase the size of the cache, the address tag decreases. So now we have an overhead of 44% instead of, if I remember it correctly, 66% before. Pros and cons of large caches. Well, it's a very safe way to improve the hit ratio, but SRAMs are very expensive. Also, larger SRAM sizes applies much slower speed. There are more loads on the signals, and the wires to get to the right place in the SRAM is much longer. And as you probably can imagine as well, a larger SRAM will also consume more power, both static and dynamic power. We're going to discuss that a little more later. So what kind of misses are removed as you increase the cache size? The other design parameter, which is maybe equally important here, is the size of the cache line. Sometimes another synonym used is cache block. So before we can really appreciate the importance of the cache line, let's talk about a different kind of locality patterns that we have in our access stream from an application. So typically we say that we have two different kinds of localities in an access stream, of addresses in an access stream from an application. One is the temporal locality. So temporal locality says how likely they are to access exactly the same piece of data again very soon. Spatial locality says how likely you are to access some data nearby the data you just accessed. Okay. So here's an example. So if the access pattern from a typical multi-nested loop application here. So in an inner loop, you touch the address A, B, and C. Then you loop back and do a new iteration of the loop. And now you access A plus 1, probably because A points to a vector, and that vector is indexed by the loop counter I. B and C you access again because they're probably local variables of that loop that the compiler didn't manage to allocate to registers. And then you do A plus 2, B, C, and so on. So here you can easily see the two kinds of locality patterns. The local variable B as well as the local variable C is accessed over and over again, so it's a high likelihood that it will be accessed soon again. And A plus 1, A plus 2, A plus 3 is accessed. So that is a spatial locality for accessing the vector A and the elements of the vector A, and the temporal locality for accessing the local variables of that in that in a part of the loop. This is just one example, but if you are a cache nerd like myself and you sit and study this kind of access pattern, what addresses is requested by an application, you could easily find these two kinds of access pattern, temporal and spatial locality. So if we like to explore the spatial locality, a good way to do here is to group data not just in words but in larger chunks called cache lines. So in this example, we're going to design a 1 megabyte cache. It's direct mapped, and the cache line size is 16 bytes, not a word. Okay, so instead we have a chunk of data here, 4 words glued together in one container, and this is our cache line, 16 bytes. Together with each cache line, we have one address tag and one valid bit. And if there's a match here between the address tag and if the valid bit is set, that means that all these 4 words are valid in the cache at the same time. Now, when we design this cache, we first have to figure out how many entries we have in the SRAM. And now we only have 64K entries because we have 16 bytes for each entry. So 1 megabyte divided by 16 comes to 64 kilobytes. We need, since we have 64 kilobytes, we have 64 entries, we need 16 index bits to index into the SRAM. We are still tossing the 2 least significant address bit over our shoulder because the CPU only asked us to provide a word, not a byte. But there are 2 bits in between here, between the words, the bits we just tossed and the index bits. And those bits identifies a word within a cache line. So by looking at the value of these 2 bits, you know whether we access the leftmost, the rightmost, or any of the words in the middle. That will be decided because by these 2 bits, because these 4 words always travel together, they're always aligned, they're always stored exactly like this in the cache. And of course, we still have to use whatever part of the address that wasn't used for our indexing as well as selection in this cache. So we have 12 bits left, and those bits have to be used as an address tag and compared with these 12 bits stored right here. Memory overhead now went down further because now we have one address tag here, and that address tag is tells whether or not 16 bytes in the cache are valid or not. So it's the 12 plus 1, 13, divided by 128 bits, so 10%. That's improved quite a lot, and the latency is still comparable to what we've seen before. So just before we go on, I just want to clarify what the job of this multiplexer is. So if the multiplexer in this, multiplexer in this example has 4 input and 1 output, and the value of these 2 select signals, select bits, will determine which of these 4 inputs is actually outputted down here. So if you have 0, 0 as an input, we may output the red piece of data, those 4 words, so 4 bytes that forms the leftmost word. If it's 0, 1, we output the blue data. If it's 1, 0, we output the yellow data. And then 1, 1, we output the purple data. So we will use this kind of multiplex boxes of different width quite a lot in this course. And of course, log 2, so it's 2 to the power of 2, 4. So with 2 select signals, you can choose 1 out of 4. Pros and cons with large cache lines. Well, what the cache lines will do is they will explore spatial locality very, very well. So if you access A and then A plus 1, then having a large cache line will really make the hit ratio in the cache much, much higher. It also fits very well with how modern DRAMs are accessed. So typically, it's a long access, a long delay to get the first word out of the DRAM, but then you can get subsequent accesses very, very quickly. So let's say it takes 10 cycles or 10 cycles to access one word, then if you access a, so you access A in 10 cycles, then you can access A plus 1 in 11 cycles and so on. We'll cover that also more in detail later on. However, if you don't have any spatial locality in your application, then this is a bad idea, large cache lines, because it's a poor usage of the SRAM. You're going to bring in lots of data that you never will access into the SRAM. Also, poor usage of bandwidth. You're going to bring data in and out of the cache for no good use. There could also be a higher miss penalty. Because sending a large cache line over wires takes longer time than just sending a single word. So typically, when you send a cache line to a cache, you typically send the critical word first. You send the word that was requested first. Also, when we start to talk about multiprocessors, we will see a phenomenon known as false sharing, and false sharing increases with the cache line size. So typically, if you look at performance as a function of cache line size, at least in a multiprocessor, there is some kind of optimal cache size. And it looks like these days the optimal cache size that's used in industry is typically 64 bytes. 32, and for all practical purposes, maybe between 16 bytes and 256 bytes are the implementations I've seen, but typical right now for x86 implementations, 64 byte is a normal cache line size. So what kind of misses are primarily removed by using a large cache line? Okay, and you know, if you look at this is a graph that one of my PhD students did a couple of years back using a tool called StatCache that we developed here in Uppsala. If you look at how the miss ratio changes as a function of cache size for a specific application, so if that application has a 256 byte line size, cache line size, this is how its miss ratio changes as a function of cache size. Larger caches is better. But if you have a smaller cache line size, for example, the blue line, this is how the miss ratio changes. So what you see on this graph here is if you design a small cache, with this specific application, if you design a cache smaller than 16 kilobytes, then it's much better to use the blue size, so 16 bytes is better. But once you start to design a cache which is larger, in this region over here, it looks like the larger cache line is better. And then when you come to this region over here, then it doesn't matter. It looks like they're the same. So what's going on here? So small cache, a shorter cache line is better. Why is that? Well, the intuitive explanation is if you have a very small cache, you can only, and your cache lines are large, then you can only fit a few of them. So you can fit a few thingies in it. And if you have too few thingies, you will not be able to explore the temporal locality that you may have in your application. So then poor job at temporal locality, that outweighs the benefit of the spatial locality. Then when you come to larger caches, then it turns out that longer cache lines are better. Larger cache lines are better. Why is that? Well, because you can explore enough temporal locality, and now we can also explore the spatial locality of the application. And of course, when the cache gets sufficiently large, then everything fits in the cache, regardless of the cache line size. So then it really doesn't matter. And just to highlight also that this is not a general truth. This is of course, this is highly application dependent, but just looking at practical cache implementation that people have done in the past, typical, you would see smaller cache line size for smaller caches and larger cache line size for larger caches.